I want to talk about optimal codes. Recall my previous lecture notes where I have talked about efficiency in lossless description of an information source. A prefix code satisfying Kraft inequality is said to be efficient. In this section, we are interested in finding an optimal code. Would the prefix code an optimal code? An optimal code shall achieve average description length, which is close to the entropy or the entropy rate of the source. So this question surely is an interesting one a student can ask. Prefix code, is it optimal? That's the question. In order to entertain this question, we want to consider calculus for optimization. Optimization here is to find a theory prefix code which attains the minimum average description length. So the problem at hand is that first, the information source is described by a random variable x. The distribution of this random variable is known, represented as px for each x in the alphabet. So px is given to you. So these are numbers. Now, we aim to find the ordered collection of description length. So described as this one. So this one should be ordered. Ordered collection of description length, which satisfies the Kraft inequality. So here, given are d, the size of the alphabet, and px, and we want to find li's. That's the problem. So we can use the calculus. And this PPT chart or slides that I have prepared for you talks about this procedure. So let us use the calculus just to have an idea. Why do I need to say this phrase just to have an idea? Because I'm going to treat a relaxation idea. The length of each code word should be integer valued, but I'm going to treat it as real valued variable. That's what I mean by relaxation, or just to have an idea. So use the Lagrange multiplier method to solve this optimization problem, where we want to minimize the expected length of code word description of alphabet. So we let L equal to expected length given as this, and then we want to minimize it. Subject to that Li satisfy the Kraft inequality. So here, as the small note indicates, we want to find Li's given Pi's and D. So that's the problem. and then we can utilize the calculus for this optimization problem. So let's relax the condition and let Li be any positive number, and then Li is basically the length of code word for each xi, and the pi is given to you, and also the size of the alphabet is given to you as m. So we want to find the collection of LIs. That's the problem. So again, I want to emphasize that D is given to you. PIs are given to you. What we want to find are the LIs. So you can use Lagrange multiplier given as this, and we take the differentiation with the each Li, which is the variable for optimization, and we obtain this. And then we set it equal to 0, and then after you have done that, you have this relation. And once I have this relation, I can substitute this into the constraint and obtain lambda, which is given to be this. So pi should be equal to d to the power of minus li. So pi is already given numbers to you, and li's are the variable for optimization. So optimized LIs using stars for optimization is given to be minus log d pi. And if I take the expectation of these optimized LIs, basically it is this, and substituting Li star into this formula, I have this. And I notice that this is nothing but the definition of Shannon entropy with base D. So that's the entropy. So expected length is the entropy. And the optimization variable LIs are given to be minus log d pi. With respect to pi, the optimized variable, then pi should be equal to d to the minus li. So in this particular optimization, li is treated to be real valued, but li has a physical meaning, which is to be the length of a code word. So it has to be integer. Since code word length must be integer, we must do the following sealing operation. So li star is optimized real valued variable, and we take the sealing operation and obtain integer valued li. In this case, the li star and li, there are discrepancy of up to 1 bit. Basically, that's the amount of deviation from li star to li. Thus, L, the expected length of description length, is greater than or equal to HDX, and equality if and only if Li star is integer, or all Li stars are integers, or in this form. So the equality part can be described by this example. Suppose that PIs are given to be this. So 1/2, 1/4, and then 4 of 1/16. In this case, the code word is given to be 0, 1, 0, 1, 1, 0, 0, and so on and so on. So this, as you can see, is a prefix free code. And the length is 1, 2, 4, 4, 4, 4. And I can take, since the distribution is given, the expectation of the description length, which came out to be 2-bit. And when we calculate the entropy, it is also 2. Basically, when I take a look at this expression of PIs, I note that this is 2 to the minus 1, 2 to the minus power of 2, 2 to the minus power of 4. So this is dyadic distribution. So this is a special case when I take the this operation, minus log d of pi. This one is 1, this one is 2. Each one of these 4 is 4, which are exactly the integer. And these integer represents the length of each code word. So this is a special case. So the definition, here is the definition of a dyadic distribution. A distribution is called dyadic if each probability is in the form of this form for each I, where n is the size of the alphabet, or the total number of code words. So the following theorem holds. The lower bound on the expected length, such that expectation of Lx is lower bounded by hd of x. And this equality is achieved if and only if the distribution is dyadic. Okay, so the proof was already given, so I just skip the proof. So the following information theoretic proof I'm going to show you. You can remind the following 3. So d and px's are given to you as numbers, so they are fixed. And then what you want to find is Lx. So the description length for each x. So that's the problem given to you to consider. And since Lx in this case is optimization variables, thus the expected length L is a variable. Note in this slide that Rx is a distribution since it sums up to 1. So what we want to prove here is that the expected length of a description of each code word is lower bounded by the Shannon entropy. So we take L minus HDX. So this is expected length, and this is the entropy with base D. And when I consider, since I have a px in common, I can consider Lx and minus 1 over px. Okay, so I can have this one in front, and then since I have an inverse and minus, I can cancel them, and then it becomes plus positive log d of px, and what's left is Lx part, and this Lx part can be represented as minus log d of d minus Lx. And I let Rx be defined as this d to the minus Lx over the whole thing over Rx, where Rx is the sum of these d to the power of minus Lx. And this R0 could be smaller than or equal to 1, satisfying the Kraft inequality. Having defined Rx this way, I notice that this part right here, d to the minus Lx, can be represented as Rx times R0. So once I have done this, then just plain arithmetic, so I can represent this way, and then I bring this to the front part, so this becomes ratio of px over Rx, and what's left is this part, and I take away the minus sign and then take the inverse inside the argument of the logarithm. So I have this. And I notice that this part is a relative distance between relative entropy, which is a relative distance between the two distributions px and Rx. So this one is non-negative. And I also noticed that R0 is a number smaller than or equal to 1. So this ratio is greater than or equal to 1. So logarithm of a number greater than or equal to 0, greater than or equal to 1, this measure here is non-negative. So I have this. Okay. We note that the optimal length for each x is in the form of Lx is equal to minus log d of p of x. If the right-hand side is not an integer, we can force it to be an integer by taking the ceiling operation for any x. Once you have the collection of integer valued lengths by forcing this ceiling operation, you can construct a DRE tree and assign code words accordingly. We have done this before, right? This DRE tree construction in our previous lecture. So the ceiling operation, what is the ceiling operation? If the argument of a ceiling operation is 1.7, for example, then the ceiling takes it to integer 2, right? If the argument was 3.2, for example, the ceiling operation gives it 4. Okay, so the deviation from this argument to the integer is at the maximum of 1. Okay, so we call such a source code generated from this ceiling operation a Shannon code. So we call Shannon code if the optimization is done by this. Okay, so since the description length for each x has at most one theory symbol additional to what's needed, the expected description length is at most one theory symbol additional to the optimal length. Okay, if d is equal to 2, then we can say that the expected description length is at most 1 bit additional to the optimal length. So here a possible procedure to find an optimal code is described, which summarizes what we have discussed so far. And the following chart talks about how to get rid of one additional theory symbol, or 1 bit if d is equal to 2, taken away using our vector processing. So the additional description length by 1 additional symbol can be taken away using a vector processing. So instead of instead of treating the source symbol by symbol manner, if we use a vector processing, so we consider group of symbols all together as a vector, and then apply source coding to each vector. Then we can get rid of the 1 additional theory symbol. So this is what we are aiming to show in this slide. And then we can just follow through the development. So here is the key part. If we do vector processing, we need a distribution for a vector, but if it is IID, these vector elements are, then the product of each symbol is the distribution of the vector. So once we have this, then we can talk about entropy of a vector. And then if we apply Shannon code to this distribution, then we can have description length, collection of description lengths. Its expectation is upper bounded by entropy plus 1 bit and lower bounded by entropy. So once we have this, since we realize that this is for a vector of length n, if we divide both sides by n, which is the number of symbols in the vector, then we can have the expected length per symbol, ln, upper bounded by hdx plus 1 over n, and lower bounded by hdx. If we let n goes to infinity, the Shannon code achieves the lower bound, which is the entropy. So this foregoing example was for IID sources. What happens if, what would be the result if we consider non-IID source? So that is the case that we want to talk about in the next slide, but same story repeats. Only measure that we have to replace in this case is that we want to use entropy rate rather than using the entropy. That's the only difference. Okay, so the message learned in this lecture is the two things list. First thing is that we can construct a Shannon code which achieves the minimum description length lower bounded by the entropy. And we can use a vector processing rather than symbol by symbol processing. Then we can get rid of the additional one symbol needed to represent our code word. So Shannon code is optimal in this sense.